Last week on Tuesday, for lab period, we went over this long worksheet and answered these questions. And so this is the lecture that if you missed any of that, you can catch up. So, although we've had really good attendance, so most people are probably caught up by now. All right, so let me just go over some things. One, we're going to assign geometries to our shapes, and what that means is that if I have a sulfur with a hydrogen and a hydrogen on it, that would look like this. If I put one lone pair on it, it'll look like this. If I put two lone pairs on it, it'll look like this. So each of these represents a bond, and it represents the number of lone electrons, lone pair electrons. The lone pair electrons are listed up here. And then there's a thing called steric number. A steric number is the number of bonds plus the number of non-bonding pairs. So here I have 1, 2, 3, 4. So I was in steric number 4, and I was with 2 lone pairs. So that's how you use the table. And then what we'll do is we'll just replace the E with the central atom, or replace the X's with the outer atoms. It turns out that this EX can be single or double bonds. So if I did S, O, O, lone pair, this would fit this particular model because EX can be a double bond, and so I would draw it like this, which I've done sort of naturally. You should put the lone pairs on the outside, but we're actually really only interested in the central atom and its relationship to the things on the outside. So we often do not see the dots because we're paying attention to what's happening here. These lone pairs, of course, are really important because they change the geometry. So we always need to see the non-bonding pairs. One more thing. By this convention, a wedge means you're coming forward. So if you have an atom here, it would be in front of you, whereas if you do these dashed lines, this means something's going back into the distance. And if you just have a straight line, that just means you're at a normal, in the plane perspective of the picture. Okay, and it's supposed to represent like a tripod with a camera on it. Next, we're going to have to choose intermolecular forces, which are attractive forces that exist between molecules. And we can have strong forces that have one set of properties, and we can have weak forces with another set of properties. The one we are going to worry about now is dissolves in water, which is what this question is asking, and doesn't dissolve in water. So what are the weak forces? The weak forces are dispersion forces. So if we have dispersion forces, then we do not dissolve in water. Weaker forces occur for all covalent compounds, so every single one of these has dispersion forces. And larger and longer molecule have stronger dispersion forces. So there's a difference between gases having weak dispersion forces and something like wax, which has a stronger dispersion force. Another type of intermolecular force or attraction is a strong attraction that takes place between covalent molecules that have a permanent shift in electrons. These are called asymmetrical molecules. And so basically what happens is, if there's a difference in the size of the molecules, the electrons will be drawn towards one side or the other. Electrons are drawn towards atoms that have properties like fluorine, very small and lots of positive charge. without having many, many layers, energy levels. So that's the kind of thing we're going to do. So we're going to look at this to figure out when is there going to be dipole-dipole and when there won't. And what that comes down to is understanding asymmetrical and symmetrical, right? And then lastly, hydrogen bonding just occurs when you have a very specific set of bonds that take place. These small atoms attached to a hydrogen create a very tight bond, intermolecular bond. And that intermolecular bond is called hydrogen bonding. If it's symmetrical, then it's only dispersion forces. So once you know that it's symmetrical, you will know that it's dispersion forces. Once you know it's dispersion forces, you need know that it won't dissolve in water. Asymmetrical, let's switch colors here. Asymmetrical has dipole-dipole and will dissolve in water. And then this hydrogen bonding is just dependent on, one more color, this hydrogen bonding is only dependent on looking for these particular bonding types, right? So if you see these bonding patterns, then you can say there's hydrogen bonding. So finally we're down to polar and nonpolar, and here it says if it's asymmetric, then it will be polar. So once we know it's asymmetric, we know it's, oops, wrong one. We know it's polar, and if it's polar, it dissolves in water, and then we always say dipole-dipole. And if it's symmetrical, then we say it's nonpolar. Then it's no, it doesn't dissolve in water, and it only has dispersion forces. Now I just need to clarify. Once you say it has dipole-dipole, let's go back. Once you say it has dipole-dipole, you also have to include dispersion forces, because remember, dispersion forces are in all covalent compounds. The dipole-dipole is only in these asymmetrical molecules. All right, so let's look at, oh, we have one more thing. Also in here is what is symmetrical and what's not. So what's symmetrical is 0 lone pairs, square planar, and linear. So these are the linear ones, and here's the square planar one. As long as all the x's are the same, these will be called symmetrical. So these are symmetrical. Let's say this is H, and I don't even know what this is. It's going to be I, and this is H. This would be considered symmetrical. But if I change this to, just change the color so it's easier to see. If I change this one to Cl and this to F, now I have two different ones, and so this doesn't meet this qualification and it becomes asymmetrical. The other big group that's all symmetrical is all of these. None of these have lone pairs. When you don't have a lone pair, that means that you can be symmetrical because everything is evenly spaced. And once everything's evenly spaced, you can end up with a symmetrical molecule. All right, so I think we've answered all the questions. Let's zoom along here and answer some questions. So the beginning is not even a three-dimensional molecule. It is oxygen, but it provided us an opportunity to reconnect with how are you supposed to create covalent compounds. So what we have is my oxygen, and then remember each of the loops represents a bond, and I move the non-bonded pairs out of the way. This is the same on both sides. That makes it symmetrical. Since it was symmetrical, it's nonpolar. Since it was nonpolar, it doesn't dissolve in water. And here, this instruction is actually cross off all those that do not apply. So we don't have these two types of bonding. We only have dispersion forces. All right, I know I did that quick. Here's SI, and it has 4 lone pairs. The number of lone pairs is the number of bonds that it should be able to have. And so here you see hydrogen has a single lone pair. And when I do bromine, it also has a single lone pair. And then I'm going to do bonding, and we'll see we get 4 bonds. And that means that we have a steric number of 4. So we're about to draw 4 bonds onto my silicon. That means it has 4. So let's go look and see what the shape will be for this molecule. So the steric number is how many bonds you have plus the number of lone pairs. So we have 1, 2, 3, 4. So we're here. Oops. How do I undo that? Drat. I don't know what happened. There we go. Ugh. So we're going to draw this shape. So we're going to come up here. Live action. I'm not editing anything. So that's the shape that I just saw. And then what I do is I put my pieces around. There's no best way to put these pieces around this model. So you can just put them in any order you want to. So my order will be H, H, BR, BR. That's it. This is 4. The name in the worksheet is Tetrahedral. Oh, this was just drawing the bonds. Sorry, this goes here. And then this is the shape. This shape has 0 lone pairs. If you have 0 lone pairs, then you're symmetrical. Oh, we're not symmetrical, are we? We're not symmetrical because we have different types of atoms, so it's asymmetrical. If it's asymmetrical, it's polar. If it's polar, it's dissolved in water, and we can get rid of this. There is a hydrogen bond, but it doesn't have one of these hydrogen bonds. We're looking for hydrogen and fluorine, hydrogen and oxygen, hydrogen and nitrogen, where the R's just represents some extension to the rest of the molecule. We don't know what it is, but we're only interested in this piece right here. All right, I think that was okay, other than me messing up what to draw there. Okay, let's try again. And this time we're going to do CO2. And so we draw 4 of them. Now at this point, it doesn't do us much good to slowly go over things, given that you can stop the video and go back and review what's happening. And one of the problems I have with this method I make of doing lectures is I can't draw on top of something and then show you a different page so that you know what, so we can look at 2 things. What happens is all my drawings disappear, and I have to rely on you to go back and look at the original drawings and compare them with pieces that were there before. So on the C, there's 0 lone pairs. There are 2 steric ones because I'm looking for X, E, X, and it doesn't matter whether this is single or double. I'm just counting the bonds. I have 1, 2, so that's steric number 2. This will have the name linear. I'll show you this in a second. And you can only draw this in exactly that way. I did say that you don't have to do lone pairs when you're doing this because we're interested in what's happening here. And you'll also see online in videos and in books, they don't always draw the double bond. They draw this shape instead because they're really interested in where are the bonds and the electrons positioned, not necessarily whether it's a single or double bond. I'd really like you to have a double bond. I think that's important. but that's, so if you please put a double bond in. This is symmetrical. No lone pairs on the central atom. Both of the outer atoms are the same thing. That makes it nonpolar, that makes it no, and that means I only have dispersion forces. All right, let's go look and see how we got linear for this shape. We had 0 lone pairs. We had a steric number of 2. So we had a steric number of 2 with 0 lone pairs. And so that led us to this, which is linear. So up here, the point is that you could have drawn this shape in this instruction, but you have to draw this shape in this instruction, right? And here you're supposed to include the lone pairs, but over here you don't have to. And you saw where the name came from, was on the thing. All right, our last one. I don't think I'm going to do anymore. Nitrogen's in the center, so it's not necessarily in that order. Hydrogen I'm going to put on this side. Oxygen I'm going to put on this side. I had several students who did this, which you can't do because you're not going to have enough bonds. You have to have your electrons spaced out as so they're as single as possible, because now this tells me that I'm going to have 1, 2, 3 bonds taking place with this nitrogen. So one's going to take place here, one's going to take place here, and one's going to take place here. So I'm going to have 3 bonds. So 1, 2, 3. And I also have, for the first time, I have a lone pair. So you're going to put 1 here. That's my lone pair I'm going to have on top. Nitrogen, hydrogen. Oh, and look, this is not going down. This is a double bond to oxygen. We're going to do our pairs. Okay, so this is not a steric number of 2. It's got 2 bonds, but if you remember, the steric number is not only the bonds, but also the lone pairs. So I have a steric number of 3 and 1 lone pair. So to use the chart, we need to look for 1 lone pair and a steric number of 3. Steric number of 3, 1 lone pair. The name is bent and it's drawn at a 120-degree angle. So let's go back up a little bit. So 120-degree angle, H, N, O, bent was the name. So for all sorts of reasons, this is asymmetrical. The atoms are different on both sides. There's a lone pair. So this is asymmetrical. It's polar. It's yes. It's dipole-dipole. It's dispersion. And it turns out that this is where the hydrogen bonding shows up. There's a hydrogen bond. It has the NH bond. It has, or we'll see an OH bond. And occasionally we see HF bonds. And so this actually has all 3. So I've just been putting a star next to the hydrogen bond so that I can tell people, yes, it has hydrogen bonding. But it has all 3 types of bonding. So this would be strongly bonded to other molecules of this nitrogen-oxygen molecule. All right, so that's how you do it. You would now have to fill in all of these. So a couple comments. Did I fix it? So it's already fixed on here. It turned out that I had made some copy-paste errors. I think it was here. I copied and pasted and left SE in here. I had also copied and pasted and left C here. And then also C on the bottom here. So just so you know, this is always right. This is never wrong. It's just, and this one, thank God, the oxygen is the right central atom, the phosphorus is the right central atom. and the SI is the central atom. So I don't think anybody had any problems. They were just telling me what I did wrong. 20 minutes, too long a video. Sorry. Talk to me, ask me questions.